Hello, this lecture will cover pages 73 through 83 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 7E, Working Advanced First Order Circuits. Before we start, I want to read something to you here on page 75. More complex first order circuits need a problem-solving strategy. The remaining first order problems in Chapter 7 will be easy for you to work out if you read, understand, and follow the step-by-step procedure on the next page. This is in your textbook, and it depends what version you have, but basically this is the step-by-step procedure we're going to follow through the remainder of the first order circuits that they have in the homework. It's a 6-step procedure, and let's take a look at these steps very closely, and I want you to follow these steps as you go through your analysis of your homework. The first thing is assume a solution for the variable x of t in the form x of t is equal to k1 plus k2e to the minus t over tau. You know x can take on voltage or current. You know what k1 is. K1 is the final value. You know what, or let's say K1 was defined as the variable at x equal infinity. And K2 was defined as the variable, the quantity x evaluated at 0 plus minus x evaluated at infinity. And you could see that down here in this final step. Step number 2, assuming that the original circuit has reached steady state before the switch was thrown, thereby producing a new circuit, I want you to draw this previous circuit with the capacitor replaced by an open circuit or the inductor replaced by a short circuit. And I want you to solve the voltage across the capacitor, VC is 0 minus, or for the current through the inductor, IL is 0 minus, prior to the switch being open or closed. That's always step 1. You assume that the original circuit has reached steady state before you throw the switch. Step number 3, recall that voltage across the capacitor and current flowing through an inductor cannot change instantaneously, and you draw the circuit valid for t equals 0 plus, with the switches in their new position. You replace a capacitor with the voltage source of the value VC is 0 plus, which is equal to VC is 0 minus, or an inductor with a current source of the value IL is 0 plus, which is equal to IL is 0 minus. And you solve the initial value of the variable, whether it's voltage or current. Step 4, assuming the steady state has been reached, after the switches are thrown, draw the equivalent circuit, valid for t greater than 5 time constants by replacing the capacitor by an open circuit or the inductor by a short circuit. You solve the steady state value of the variable x of t after 5 time constants. You know that's going to be x of infinity. It's going to be voltage at t equal infinity, or it's going to be current at t equal infinity. You know to calculate the time constant. Since the time constant for all voltages and currents in the circuit will be the same, it can be obtained by reducing the entire circuit to a simple Thevenin equivalent circuit at the terminals of the storage element, whether that be an inductor or a capacitor. The time constant for the circuit containing a capacitor is tau is equal to R Thevenin times C, and for the circuit containing an inductor, it's tau is equal to L divided by R Thevenin. And then finally, step 6, using the results in steps 3, 4, and 5, we can evaluate the constants in step 1 as K1 is equal to x of infinity and K2 is equal to x of 0 plus minus x at infinity. We derived these 3 times before in previous pages or lectures, and hence the solution as discussed. Now, this might sound a little confusing as I read through these 6 steps, but we've been doing this all along, and it'll make sense as we go through some problems. Let's take a look. On page number 77, example problem number 3. In the book, it's example 7.3 on page 263, which is the textbook I have. But needless, whether you have this version of the textbook or not, here's the problem. There's a 36 volts source out here, plus to minus. There's a 2K ohm resistor up here. There's a 6K ohm resistor at this point. There's a 4K ohm resistor here. There's a 12 volt source out here, plus to minus. The capacitor's sitting right here at 100 microfarads. And this switch is opened. The switch is going to be open for a long period of time. And then you're going to close it at t equals 0. And I want to find the current I at t for t greater than 0. Well, it's going to require looking for initial conditions, but that's what these initial steps will do for you. So the first step, assume the solution in the form I at t is equal to K1 plus K2e to the minus t over tau. You don't say x at t. We're solving for current. So right away, step 1, you write this down. I at t, x is I. I at t is the form. You get credit for that. Second step, the initial voltage across the capacitor is. Read step number 2 very carefully, and there's my analysis of it. I end up with VC is 0 minus is equal to 32 volts. Step 3, remember, voltage across the capacitor can't change instantaneously, so VC is 0 minus is equal to VC is 0, which is equal to VC is 0 plus. You use that in this problem. VC is 0 plus is equal to 32 volts. Therefore, the current at 0 plus is equal to 32 over 6K, which is equal to 5.33 milliamps. Remember that I is 0 plus is equal to K1 plus K2. This is all part of step 3. Remember that right there. That's important. And here's your I is 0 plus. You're going to use this, 5.33 milliamps in step 6. Step 4 says find I of infinity, 4.5 milliamps. Remember that I of infinity was simply equal to K1. Step number 5, find Thevenin equivalent resistance. As seen by the capacitor in this case. It's 1.5 K ohms. The time constant calculates to be 0.15 seconds. Step number 6, we know that I is 0 is equal to K1 plus K2. We know I of infinity is K1, therefore K1 is equal to 4.5 milliamps. We already calculated that I 0 is equal to K1 plus K2. So now you can find K2. K2 is 8.3 milliamps, which leads us to the final form. I at t is equal to 4.5 plus 0.83 e to the minus t divided by 0.15. Now I don't care if you invert 0.15 and you put it in the numerator. If you do that, you're going to end up with 6.67, a negative 6.67 t up here. Either way, it'll work out. And there's your answer. But before you move on, let's evaluate this and see if I is 0 is 5.33 milliamps. So go ahead and put a 0 in for t and make that evaluation. And then put infinity in for t and evaluate it and see if you get 4.5 milliamps. If you do, that satisfies those two conditions, one of which we calculated earlier. Well, both of them we calculated earlier in our analysis here. The 5.33, if you look back, we calculated that back in step number 3. In this 4.5 milliamps, we calculated it up here in step 4. Good check on your work. Example problem 4. Here's the circuit. We have 20 volts out here. We have 12 volts here. We have an inductor. And what we want to do in this problem is we want to find the value of I sub R here through that 6K ohm resistor. The switch is closed up here at this point for a long period of time. That's going to get you through step 2 to 3. That sets up an initial condition with the current over here. And then what, with the current here, but more importantly with the current here, because that's what we're looking for. And at t equals 0, you open that switch. So I want you to find I sub R, a t, for t greater than 0. Step number 1, there it is. Step number 2 results in this 1.33 milliamps. Read step 2 and make sure you understand you have to redraw this circuit, and that's what it looks like when you redraw it. Step number 3, there's the circuit, which results in IR 0 plus is equal to negative 1.77 milliamps. K1 plus K2 is equal to a negative 1.77 milliamps. We're going to use that later. Moving along in this problem, step number 4. There's step number 4 resulting in K1 is equal to a negative 0.8 milliamps and K2 is a negative 0.98. Step number 5, finding the time constant. 1 microsecond. And step number 6 is making the substitutions in. What substitutions are you making? You're making the substitutions from, in this case, these values here and here and here that you found previous in this problem. The current with respect to time in that circuit, I of R, is equal to a negative 0.8 minus 0.98 e to the minus 1 times 10 to the 6t, and that's in milliamps for t greater than 0. And this is what that current looks like. It's a step response, don't forget. We're not talking about the current in the inductor, we're talking about the current in the resistor. It's 0.67 milliamps from negative infinity up to the time you throw that switch. When you throw that switch, it drops down to a negative 1.78 milliamps, and then there's a discharge back to negative 0.8 milliamps. If you look at that circuit, I think you'll see why there has to be a current there. There has to be a current, I sub R, through infinity. Problem number 5. Again, we have a 10 volt source out here, plus to minus. The switch is going to be closed. You have a 4 amp current source here in that direction. In this problem right here, we want to find I of L at t for t greater than 0. We want to find this current out here through this 2 Henry coil with respect to time. We have a voltage-controlled voltage source down here. That's not going to make too much difference in this analysis. You'll see that in a minute. And the controlling variable here is V1 of t, which is the voltage from this point to this point, which is basically this node voltage from here to ground. I called that V1 of t. At least the author did. That's an inductor. We want to solve for current here. So here's your step 1, make an assumption. We're solving for current, so T is equal to K1 plus K2e to the minus T over tau. Here's our step 2. Read through step 2 and make sure you can see that. Kirchhoff's voltage law around the outer loop. Here's step 3. Here's step 4. I worked through step number 5 using Kirchhoff's voltage law. I want to solve for V1. The whole purpose of this, solving for V1, coming up with two equations. I want to find out IL down here. IL is equal to 2 amperes, which is equal to I of infinity, which happens to be the K1 term. Found the quantities I need, so I plug them in step 6, and I end up with ILT is equal to 2 plus 3e to the minus t over tau. Need to find tau here yet. We have to find tau in this problem. Well, we know tau is equal to L over R Thevenin. We have to find R Thevenin, but remember we run into a little bit of a problem here. Not a big problem, but a little problem. We have to reduce all the sources here to 0 normally, and we look back in to find R Thevenin. But you can't do that technique. You can't do that technique when you have dependent sources. We talked about this a while back. When you're finding R Thevenin and you have dependent sources, the only way you're going to do that is through this formula here. It's a two-step problem. You have to find the open circuit voltage, which is E Thevenin at this point, and then you have to find the short circuit current, which is Norton current. You have to form that ratio to get R Thevenin. This works all the time, by the way, but you have to use this technique, V open circuit divided by I short circuit, right out here, to find R Thevenin when you have a dependent source, one or more, in a network like this. So there's my open circuit voltage calculation up here. I get 48 volts. I want to find the short circuit current. It's just another problem. Short circuit this, and there's the problem here, and there it is. I could use nodal analysis. I can use loop analysis. I ended up using nodal analysis at that point. I find the short circuit current. I find V1 is 4 volts. Through nodal analysis, I get 2 amperes flow in there. So I know my 2 amperes, and I know my 48 volts. I get 24 ohms. There's my Thevenin resistance. Now I can find my time constant, 0.083 seconds. I inverted that and I put it in the numerator here, and my final answer for this problem is IL of t is equal to 2 plus 3e to the minus 12t, and that's in amperes. I like this problem, and I'll tell you why I like it. Because it's relatively complex. If you take a look at the circuit, it's relatively complex. But it's not a difficult circuit to analyze if you just follow those steps. And you have to try this on your own. You really have to. These last 3 problems I've shown you, the best way to work these problems is write down the circuit and write down what I want you to find. And then just have this in front of you. And you follow this procedure. And when you're done with each step, you take a look at my analysis. Because if you look through here, it's not the same thing. You have to try this on your own. All 3 problems I want you to do on your own, work at each one of these steps through. But I continue to like this last problem because it has that dependent source. And to find the Thevenin resistance so you can calculate the time constant, it requires this technique which we discussed in a previous chapter. These problems really aren't difficult, but you just have to use this strategy. And like I said when we started this out, I made the comment that more complex first-order circuits need a problem-solving strategy. So all these problems, I think, will be easy if you read, understand, and follow the step-by-step procedure that I've read through. And that concludes the lecture.